Hi, this is Dr. Vev. In the previous video, I introduced the principle of mathematical induction and showed you how to employ it to establish formulas that are known to be true. In this follow-up, I will show you how you can use the principle of mathematical induction to establish more abstract types of statements. For example, the first problem I wish to consider is to show the sum of three successive cubes is divisible by 9. Now let's recall what the principle of induction actually says. It says that if you have a statement S of m and it's known to be true for small values or values m less than k, and it can be shown that S of m implies the truth of S of m plus 1, then it must be that the statement is true for all values of the integers. Now, how do you apply that to something like this? So first of all, we have to understand what's meant by successive cubes. It just means that you take a cube m minus 1, the next one to that would be m, and the next one to that would be m plus 1. So this thing has to be divisible by 9, so I would just write it as 9 times some other integer k, where k is another integer which I'll call z. So the base case should be tried, and these values less than k are called base cases. So we have to try just one or two base cases will be enough. Let's try m equals 1. So I'll get 0 cubed plus 1 cubed plus 2 cubed, which is 9, and that's certainly 9 times 1, so that is true. Let's try m equals 2. That's going to be 2 minus 1, or 1 cubed plus 2 cubed plus 3 cubed. So that's 1 plus 8, 9, plus 27, which is 36. And 36 is 9 times 4. So that's for k equals 4. So you get a sense that this must be true for all values. So we're going to assume the statement S of m and show that S of m must be m plus 1 must be true. So what is S of m plus 1? S of m plus 1 is a statement that m cubed, so all I'm doing is advancing the integer by 1. So m cubed plus m plus 1 cubed plus m plus 2 cubed. Now if I show this is 9 times an integer, I'm done. In establishing results like this, you have to use the assumption S of m at some point. But S of m has got m cubed and m plus 1 cubed. So I can use S of m here. I cannot do anything with m plus 2. I just have to keep it as it is. So if I use S of m here, I can write m cubed plus m plus 1 cubed as 9k minus m minus 1 cubed. And then I still have m plus 2 cubed for the ride. Let's do some algebra and see if this can be simplified. That's 9k minus a minus b cubed can be written as a cubed minus 3ab, 3a squared b. So here b is minus 1, and that's why you get the minus sign, plus 3ab squared. When I do ab squared, I'm going to just lose that minus 1, so I'll just get 3m, plus b cubed, and minus 1 cubed is minus 1. And I'll do the same type of expansion. So there's some algebraic grunge work here. A plus b cubed again, so that's a cubed, plus 3a squared b, so 3 times 2 is 6, so that gives me 6m squared, plus 3ab squared, so that's 3m times 4, or 12m, plus b cubed, meaning 2 cubed. Let's see what we can get from this. When I simplify, I get 9k. Fortunately for me, I'm losing some of these powers. That's a plus 3m squared because of the two minuses, and that combines with a 6 to give me plus 9m squared. Here I have a negative 3m and a 12 plus 9m. And here I have minus of a minus 1 and an 8 plus 9. So amazing, you've shown that it's equal to 9 times something. We don't care what it is. If k is an integer, then k plus m squared plus m plus 1 is also an integer because m was assumed to be an integer. So this whole thing is 9 times some other integer which I'll call L. So we have established the inductive step, and so the statements must be true for all values of, for all successive 3 cubes. So that's a way of proving something like this. Let's try another problem which establishes an abstract statement like this. I would like to show that n times n plus 1 times n plus 5 is a multiple of 3. So that's problem 2. How would you solve this problem? Well, first of all, we have to make sure that the base case works. If the base case does not work, then there's nothing to do. So let's try that. So first of all, let's keep the statement S of m. The S of m is that n times m times m plus 1 times m plus 5 is equal to 3 times k, where k belongs to z. All right. Let's try the base cases next. Let's try m equals 1. Then I have 1 times 2 times 6. Well, that's 12, and that is 3 times 4, so that works. Let's try m equals 2. That's going to be 2 times 3 times 7. 7 3s are 21, 21 2s are 42, and 42 is 3 times 14. So that works too. All right, now let's try to show the truth of the statement S of m plus 1. To establish S of m plus 1, we need to work with the left-hand side. That's equal to m plus 1 times m plus 2 times m plus 6. All I've done is replaced m with m plus 1. Now that should be made to look like 3 times something. Okay. Unfortunately, if I want to use the inductive hypothesis, that has got m times m plus 1 times m plus 5. You see that only m plus 1 is there. You don't have m or m plus 5. How do you do this? So one step is to just proceed by simplifying and see how far we can get. So I'll write m plus 1 and see what I get if I multiply these two. I'm going to get m squared plus 2m plus 6m, or 8m, plus 6 times 2, 12. And let's see what I can do with this. Can I write this in some fashion that's similar to that? Well, actually I can. In fact, I can write the square bracket as m squared plus 5m plus 3m plus 12. Now, this way of writing it was inspired by the necessity to somehow use m plus 5. I need to use m plus 5. I don't have a 5, so make it happen. And let's see what happens after that. Okay, so this is a trial and error process. There's no surefire way of doing these things. You just do it and see if it works or not. If it doesn't work, you try something else. So then you have m plus 1. Now at this point I'll write this as m plus 1, and here I'll factorize m times m plus 5. So that part's looking good because I have m plus 1 and m plus 5. m plus 1, m plus 5. What about this part? This is going to be 3 times Well, I'll just write this as 3 times m plus 4, which it certainly is. Okay, so I'm going to get m times m plus 1 times m plus 5, which I can simply write as 3k. And here I'm going to get 3 times m plus 1 times m plus 4. I no longer care if what this is, because as long as I have that 3, I'm home free. So I can take the 3 outside and write this as k plus m plus 1 times m plus 4. Now if k is an integer, which it is by assumption, and m is an integer, which it is, m plus 1 times m plus 4 must also be an integer, and k plus all that must be another integer. Let's call it L. So we have shown that the inductive hypothesis is true, and so the statement must be true for all values of integers by the principle of mathematical induction. So in this way, we have shown another abstract statement using the principle of mathematical induction.